Completing the square to standard form. This video will cover when we have equations of circles that are in formats that do not allow us to easily identify the center and the radius, and taking those formats and manipulating them so we do get our standard form equation, which does allow us to easily identify center and radius. So as a reminder, our standard form looks something like this. X minus h squared plus y minus k squared equals r squared, where we know the center is hk, and the radius is just the square root of that last term. Okay. So how can we get from an example that I have shown here to something that looks like this? The way we do that is through completing the square. So I'm going to cover the geometric interpretation of completing the square, and along the way, we'll show the algebra and see how that process will get us from what we have on the left to something that looks like what we have on the right. So in these scenarios, you can see that there are quadratics in these equations. And in general, to complete the square, you're going to have to go through a process that is easily viewed through its geometric interpretation. Because we are in a geometry class, it's nice to look at that. So what is completing the square useful for in algebra class? Completing the square will be used to actually solve quadratics, but its other purpose is to actually just manipulate the equation and how it looks. And that's the purpose that we want to utilize today. So take some quadratic of the form x squared plus bx. What's important with completing the square is that the coefficient in front of the quadratic term must be a positive 1 for this to work. And we're going to look at this again from its geometric perspective, where x squared looks awfully similar to the area formula for a square of side length x. So imagine I have a square x by x. Its area formula would be x squared. The bx looks awfully similar to an area formula for a rectangle that has length x and width b. So if I take that algebraic interpretation of that quadratic x squared plus bx and I draw the geometric interpretation, we have what we see here. Now, here's what we're going to do. We're going to take this rectangle that is b by x, and we're going to split it right down the middle. And we're going to take each part, and we're going to tack it on to this square. And it's going to fit right along the sides because our rectangles have length x, which is the same as the length for our square. Now, because we split it right down the middle, the width of these rectangles is now b over 2. So you can see what we have now is this square and two rectangles. And what we are interested in is how do we complete the square that's being outlined in green. So what must we add on to our equation to finish off this square? So we have the area formula for a square plus the area formula for two rectangles, and we want to figure out, well, what would the area formula for that little square in the bottom right be in order to complete the square? Well, we know that little square has dimension b over 2 and b over 2. So we should add b over 2 squared, which would be the area formula for that square. And this here, the process of adding b over 2 squared to that quadratic is the act of completing the square. So that's where it gets its name, and it's a nice geometric interpretation that you can see. Now, why are we interested in that? So now we figured out that to complete the square on the quadratic, we must add b over 2 squared. So this is our completing the square part. But what does this equal? So what is this? What I have here, this looks nothing like something over here. So it seems like it's not very helpful. But let's go back to our geometric picture here. So we know one way to represent the entire area of that green square is this. Is there an equivalent way to represent the area of that square? Well, we know the area of a square is just the side length squared. So the side length of our new square is x plus b over 2, right? X plus b over 2. So an equivalent way to represent the area of our green square is x plus b over 2 times x plus b over 2, which can be written as x plus b over 2 squared, where x plus b over 2, again, represents the side of our square. And you can see this little piece, this thing squared, looks awfully similar to this or that. And that is why we use completing the square, because we can take something that it looks like a messy quadratic. We have a quadratic and a linear term, which we are going to see in a second in this example, and manipulate it so we get some term squared. Okay? So I think the geometric interpretation is nice intuition on why this thing works, instead of just blindly accepting that you just add b over 2 squared to complete the square. It's nice to know where that comes from. And the name is because you are literally completing the square. Okay, so now let's jump back to our example and show how we're going to use completing the square to get a standard form equation. Well, to complete the square, we said that the coefficient in front of the quadratic term must be positive 1. But what's unique about this example, or different about this example than what we just looked at in general? Well, we have two quadratics here. We have an x squared and we have a y squared. So all that means is we're just going to complete the square twice. We're going to handle the x squared in the x term as one problem, and the y squared in the y as its own other separate problem. Now to do this, we saw that our general introduction was something of this form, x squared plus bx. So you'll notice that we want what we're going to, you will notice is we want something of that format. And what we have in this equation or this example is not something of that structure. So we're going to manipulate this equation by moving all the variable terms to the same side and the constant terms on the other. Because when we looked at x squared plus bx, there's no constant term involved and no constant term needed to actually complete the square. All we want to look at is the quadratic term and the linear term. So I'm going to move the x squared and the y squared and the 6x all to the left, and I'm moving them that way as opposed to moving the 22y to the right and the 123 to the left, because I want positive quadratic terms, because we need a positive 1 coefficient. So it's going to be x squared, and I'm going to do x squared x, y squared y, so I can distinguish them as two separate pieces. So we have our variable terms separated from our constant terms. And now we can see that I'm going to treat this as its own little quadratic and this as another one. And I'm just going to complete the square twice. So let's look at the x squared plus 6x first. To complete the square, we know we must add b over 2 squared to both sides. Now the b changes depending on what quadratic you look like. So don't use the same b throughout the whole problem. That's why we want to split these up into kind of its own sub-problem. Our b value is whatever the number is in front of the linear variable term, our constant coefficient to the linear term, which is positive 6. So if we divide by 2, we get 3. If we square it, we get 9. So we're going to add 9. That's how we complete the square on the x. Now, if I'm going to complete the square with the y's, my b term is now positive 22. Divide that by 2, I get 11 squared, I get 121. So we're going to add 121 to complete the square on the y quadratic. Now, because we're working with an algebraic equation, we must keep this equation balanced. I can't just add 9 and 121 to the left side without doing it to the other side. That way I can keep the equation's integrity and not change its actual value in the end. So that is another common error. People forget to add the b over 2 squared to both sides. Remember, we're dealing with an actual algebraic equation. Before, when he introduced it, we were just looking at an expression. So we want to keep our equation balanced. Now, we still want to treat these quadratics as their own individual problem. And the purpose of completing the square is to produce what we call a perfect square trinomial, which means when we factor this quadratic, we should get a duplicate factor pair. And in fact, just a reminder of factoring, what multiplies to that constant term 9, but adds to that linear coefficient 6. So it multiplies to the last term, but adds to the middle term. We're going to get positive 3, positive 3. And if we were to execute a double distribution here, you would get x squared plus 6x plus 9. So we know x plus 3 times x plus 3 is equivalent to that quadratic expression above. And because we have the same thing multiplied by itself, we could condense it down to x plus 3 squared. And when we introduced the completing the square process, we saw that the equivalent format for our quadratic was x plus b over 2 squared. And the b over 2 value is 3, so that is supported here. We're going to do that same thing on the y quadratic. What multiplies to 121 adds to 22. You're going to get plus 11 plus 11. You can condense that down into y plus 11 squared. And again, that shortcut that we saw as another way to represent the area for our square was just x plus b over 2 squared. We can see that that constant value that appears at the end is in fact b over 2. Now remember, there's a plus in between here. And then at the end, we're going to condense this all down. And that equals 7. So we went from this at the beginning down to a standard form equation for a circle. And we would say we have center, negative 3, negative 11, and the radius is the square root of 7, right? Make sure you're taking the square root of that constant term. So let's summarize the process. So how do we complete the square to go to standard form? The first thing you want to do is separate the variable and the constant terms. And when you make the separation, you want to make sure that your quadratic terms have a positive 1 coefficient. Okay, if that is not the case, you will not be able to correctly execute the completing the square process. Super important. Okay, so if you have a negative 1 in front, not going to work. If you have a different number in front, you're going to have to divide through by that value as long as they're both the same. But we're not going to make them complicated in that sense. Usually they're going to have a coefficient that are both the same, so you could divide both of the sides of the equation by that value to get that positive 1 if necessary. But the point is, you need to have a positive 1 coefficient to execute the completing the square process. So that's your first thing. Separate the variables and constant terms. Have a positive 1 coefficient for the quadratic terms. And you just want the format structured so that you can work with two subproblems, essentially. So you want something like x squared plus ax plus y squared plus bx, or sorry, by equals c. So something like that, right? So you have this quadratic that you can complete the square on, and this quadratic to complete the square on. So if you don't have it in that format, make that the case. Step 2, once you have it in that format, you're ready to complete the square, which is the process of plus a over 2 squared for the x in this case, or plus the b over 2 squared for the y in this case. And remember, to add to both sides of the equation. Okay, keep that equation balanced. If you don't add your a over 2 squared or your b over 2 squared. Now, why am I saying a over 2? Because I'm using a for this particular general format and b here. So a over 2 squared for the x, b over 2 squared for the y. The reason I'm using different letters is to show you that they're not going to be the same number like we saw in the example above, okay? So just essentially take the coefficient in front of the linear term, divide it by 2, and then square it. That's what you're adding on to both sides. And if you forget to add it to the other side, your radius in the end will be wrong. So you'll actually still be able to identify the center correctly, but your radius is going to be thrown off. Now, once you have that completed, you're going to factor or use the shortcut to in standard form. So once you have the x squared plus ax plus a over 2 squared plus y squared plus by plus b over 2 squared equals c plus a over 2 squared plus b over 2 squared. So I'm adding it to both sides. So here's our completing the square part. We want to get this thing factored, and the shortcut is we're just going to have x plus a over 2, whatever that a over 2 value is in that case, plus y plus b over 2 equals the sum of these, which we'll just call d, and we'll be able to identify the center and the radius off of that, okay? So if you forget the shortcut, no worries. You should still be able to handle the factorization of that quadratic. The question you're going to ask yourself is, what multiplies to that constant term and adds to that middle number attached to the linear term, right? So if I go back to the example before, for the factoring, if you don't know the shortcut, which is completely fine, what multiplies to the constant term but adds to this linear term? Positive 3, positive 3. What multiplies to the constant term, 121, but adds to the linear coefficient, 22? Positive 11, positive 11. And due to the nature of completing the square, you should always produce a duplicate factor pair. So when you ask yourself that question, the two numbers you come up with should be identical. Because if they're not, there's no way to take your factorization and condense it down into that thing squared, which is ultimately what we want. So don't forget the end goal. We want an equation that looks like this so we can identify the center and the radius. So there's a video on how to complete the square to reach a standard form equation for a circle.